Hello everyone, welcome to week 3. This week we will cover hierarchical linear models and longitudinal data analysis. All of these models that we will talk about fall within a general model called the mixed model. And depending on the tradition that you work in, for example, if you're in psychology or in education or in sociology, or even in medicine and other fields, they use different names for these types of specific regression models. Sometimes people call them multi-level models, others call them hierarchical linear models or HLMs. If you talk to econometricians, they call them random effects or fixed effects models, and so on. And they have different names, but then statistically, or the type of method that we use to analyze the data are the same, and they generally are called mixed models or mixed effects models. And we will use this general framework to analyze these types of nested or longitudinal data. So this week we will cover this nested data structure. For example, if you have patients who are nested within hospitals, or learners who are nested within residency programs, or multiple measurements of the same learner over time. So that's longitudinal data analysis. So these types of nested data structures require us to use a different type of model, which we will call, in general, mixed models. So here we will first begin by looking at analyzing hierarchical or nested data. So let me give you some examples. So for example, here we have this example where we have three families, Kim, Lee, and Park. These are Korean last names. So for example, and let's say there's two kids per family. So you have A, B who are within Kim, C and D who are within Lee, and then E and F who are within Park. And so you have children nested in families. And you can see a similar design for other types of structures where you have patients nested within hospitals, learners within educational programs. And the idea here is that there's some of a correlation within individuals nested within a larger family. So you would expect patients within the same hospitals to be somewhat similar, or learners within the same residency programs to be somewhat similar. So you want to account for this within group clustering. So that's what we're trying to do. And let me go over, in the next few slides, I'll go over some a bit of theory, so just to give you some statistical framework, and then we will go over several examples so that you can see some applications of what we were talking about in this week. So if you recall from the previous week, we had this, we talked about linear regression models, and the assumption for linear regression models is that for each observation in our data, for each learner or for each patient or each observation, they're independent of one another. So, so here we have the standard model. Y equals some beta plus error, epsilon, and we assume that this error is independent for each of the observations, and that the errors are normally distributed with mean zero and some kind of standard deviation. This is a statistical framework that people use. Now, if we talk about a nested model, we now have several measurements, or several different measurements of the same learner. So for example, if we're looking at patients, or if we're looking at multiple longitudinal data analysis, for example, and you have the same learner measured over multiple occasions, let's say you measure them over 2 occasions, first I would be the first measurement of the first learner, and then you have the second measurement of the same learner, and so on and so forth. And so if you have this nested structure, we now violate this general standard regression model, because we now have multiple observations for the same learner. In other words, there's some correlation. So this assumption here is no longer satisfied. So where I'm going with this is that basically we have to account for some dependence, and so we have to introduce this new term here, zeta. So y equals beta plus some zeta, and then this error term epsilon. And so this is the people will report different types of multi-level or nested data analysis, in essence, they're introducing this new parameter so that we can account for this violation in the statistical model. And if you're talking about G-theory designs, others, it's using the basic same principle. We'll talk about this again. We'll revisit it when we talk about G-theory and other types of nested designs in weeks to come. All right, so that's the basic idea. And so here, let me give you a sample data here. Here you see 17 different candidates or 17 different learners, and there's 2 measurements of the same learner over different occasions. And so here, this is your J's, and this is your I1 and first I, and then the second I. So you can see that we no longer have independence, and we have this nested structure. So you can see that there's correlation between these 2 occasions. See, they're very close to one another, meaning that that they're dependent. So going over this a little bit more, you see that when in this equation y equals beta plus zeta plus epsilon, we have this population mean, which is the beta, and you have to account for this difference. So this zeta j, you see this j is your subject or subject level differences. So we not only have to account for this error term, we also have to account for these subject level differences. So talking about it a bit more, if you talk about just a standard regression model, all we're concerned about is this first distribution. So we try to, in the regression model, it's estimating this beta parameter, and all it's trying to do is to identify this distribution for your group of subjects that vary by this much. But now we have multiple observations, so it not only has to account for this, it has to account for these 2 different factors. So I'm explaining all of this to you so that you have some sense of what's going on in the background of Stata, because Stata, I mean, it's really easy to run the analysis, it's really easy to type the syntax, and it's going to give you these output, but it's important for us to understand what's going on in the back end. All right. So basically, just like we assumed that the error term epsilon was distributed using some kind of a distribution, we're now going to assume that this zeta term has also this distribution. And in a mixed effects model, or in a hierarchical linear model, or in a multi-level model, again, these are different names for the same approach that we're using, and they're all called mixed effects models. Now we're assuming that this is distributed within some kind of distribution. So if you were to take a statistics course, I mean, they'll spend this entire semester talking about these different concepts, but we'll stop here in terms of the theory, and we'll jump in to some real examples. All right, so let's open a one example data set. This is the hospital data set that I have uploaded on Blackboard. Okay, so let's here, and we'll open this example here. All right. So here in this data set, we have the hospital ID, patient ID, we have some outcome variable, we have some predictor, we have some independent variables here as well. And if you look at the data, you can see that you have different hospital IDs. So this is all the same hospital ID, and this is the patient ID. So you can see that there's patients nested in hospital, and you have these variables here. Okay, and the hospital type is basically just non-academic, academic, or community level hospitals. All right, so I'm sure you deal with data structures that look like this, that have some nested structure. All right, so let's do tabulate hospital. Again, for tabulate, this would be, you can go to here and you can look at frequency tables, or you can type tabulate hospitals, and this will just give you the distribution of hospitals. So you can see that there's a total of 65 different hospitals in this data set, and depending on the hospital, you have anywhere between 73 patients 102 patients, 198 patients, and so on and so forth. So this is certainly a nested data structure, right? So if we were to use our usual approach, so if we do regress outcome, which is your dependent variable, and then your predictor, which is your independent variable, this is how we would have done this analysis last week, and we would have seen that, you know, on average, this predictor, this is the intercept, and this is for every unit increase in the predictor, the outcome variable of some patient outcome increases by about 0.60 units. And so this is how we would interpret the data. But now we know that, you know, this would violate the general statistical assumption of the model because we have nested data structure. So this, if you were to report this, this would be a flawed result, or this would be a biased result. Okay, so so this is the exact same outcome that I have replicated from this data screen. You know, you could look at the R squared, and you could look at the F statistic, but again, this is flawed because it does not account for within hospital or this within group nesting structure. So what we have to do is we have to use this mixed regression, and what I would do is to use the syntax option in Stata. So this is, we're going to use this Stata command called xtmixed. Okay, so I think it's good for us to start knowing the syntax. So I'll refrain from using the menu options here, but you can go to statistics, and you can go to multi-level mixed effects model, and you can go through it here as well. But let's use the syntax. So xtmixed, and then we have outcome predictor. And so until here, it's exactly the same. And we put two of these bar lines. So if you're using a computer, this is a shift backslash key just under the backspace in most computers. And then we have to put the grouping variable, which is your hospital, and you put a colon here. And then we're going to put comma MLE. So MLE is a estimation option. It's called maximum likelihood estimation. It's okay if you don't put this, but it's probably better if you put this. Generally, people do put this option. So this is the syntax. So basically what this means is that we're going to run a mixed effects model. This is your dependent variable. This is your independent variable. And if you want to put more independent variables, you can, you know, certainly type female and other things here as well. And this is your grouping variable. And then you just put a colon at the end here. You press enter, and you see this thing that will come out. So it shows you that, you know, you have about, you know, 4,059 observations of data. You have 65 hospitals. On average, there's going to be 62 patients per hospital. You know, anywhere ranging from 2 patients all the way through about 198 patients per hospital. All right, and you can see that the predictor is very similar to what we had before, but the intercept, you can see, is quite different. Earlier, if you recall, the intercept was negative 0.01. Now we have an intercept of 0.02, and you can see this other output that's produced here. Basically, this is your standard deviation of your intercept. Okay, and I'll talk more about this. And then this is your residual variable. So this is like the zeta term that we talked about earlier, and then this is your epsilon term that we talked about earlier. So how do we interpret all of this? So we go back here. If we go to the next slide, you know, the average intercept is 0.02. But then, depending on the hospital that you're from, you know, there's going to be a whole range of different intercepts that you have to deal with. So the 95% range of hospital intercepts is 0.02 plus minus 1.96, and this 1.96 is the term used for 95% confidence intervals, multiplied by 3.04. 3.04 is here, and so you see that the range of intercepts is anywhere between negative 5.9 all the way through 5.98. So that's what you can see as the intercepts.